should have definitely have a doubt why we should use. So I'll just show you some slides on what is available inside the Intel FPGA as resources that will help you to be fine-tuned for artificial intelligence and machine learning applications. So that we have quite set of tools which are meant or fine-tuned for AI and ML. So you can see that the Intel page, if you open, they say Intel AI everywhere. Right? So this year and next year our caption is always AI. So that's the plan. So that means it doesn't mean that you are forced to learn AI. We are just enhancing, right? Where we are seeing opportunities where we can use AI. That's the objective. It doesn't mean that everybody is pushed to learn AI. Right? The objective is like you know hardware, that's fine. But then how do you use this FPGA as a hardware inference engine? How do we use that? Okay, and why do we require that? Right? Now let's just think what is present inside the FPGA and how that could be used for SOC applications or AI applications. Okay? Again, you can stop at any point of time if you have any questions. And the slides are very simple for you to understand. If there are any specific queries on that or if you require more details, I'll show. In the afternoon, I'll share you some specific slides which are a part of the university program which can be accessed as free resources for the faculty as well as for the students. So we have tools which are called as one API. We call that as one application programming interface. That means you know that Intel has CPU, it has GPU, it also has FPGAs. Now what is the problem? You have one person writing the code in C or C++, other person writing the code in Verilog or VHDL, right? Then you need to take that into different platforms, right? A person who writes something in the CPU logic may not know what happens in the FPGA. So what is our basic thought process? We come up with a heterogeneous computing, an high performance computing. We call that language as SYCL, which is a data parallel C++. Because you know that the programming languages are sequential in nature, whereas the hardware description languages are concurrent in nature. But then you need to bring one language that can be taken to CPU, GPU as well as FPGA. Then how it is possible? That's the basic thought process. Now only one code we are going to write, which is SYCL, and the same code can be taken to CPU, GPU as well as FPGA. And we also have a tool called OpenVINO, which is called as Open Visual Inference and Neural Network Optimization Toolkit. So that means the students should have a fair idea of machine learning course, and then they should also learn something on deep learning if they know. We have a course called Accelerate Deep Learning using Intel FPGAs. Right? That means what is the basic thought process? If the students have a background of artificial intelligence, a basic course on machine learning, they can understand how that can be used in the hardware. That's what we call that course as a hardware accelerators for AI. So now what is the, is that free? When you say yes, the tool set is free, which the professor can definitely try. And what is the add-on advantage? The professors can also get access to the solutions, whereas for students it is just an assignment. Right? So that means what is the basic thought process? With that solutions, you can also build your own set of assignments and then extend it further. It doesn't mean that whatever given by the university program you should use that one. You can reuse that and you can customize it and use it for different applications. What are available? There are reference designs, there are reference examples which are available in the same website. We have put that in the GitHub site, so it is available for public. Right? So you can just go through that GitHub site and get the things done. Okay, what are the topics? FPGA architecture, I'll spend some time. Why SOC FPGAs, we should know that. And what is the meaning of hard processor system? That means you have a third-party processor from ARM that you are immersing into the Intel FPGA chip. So the FPGA is from Intel, but the processor is from ARM. But then both are present in the same chip. That means you need to understand that, okay, I wanted to use only FPGA, you can still use. I want to use only the ARM section without touching FPGA, yes, we can do that. No, I want to make communication between FPGA and ARM. We can do that, no problem. So now the application can be widened. Why? When you say you don't have two different chips, both are present in the same chip. That's the process. I'll just show you what is the basic background. Then, what are the different HPS that are available. Because it doesn't mean that, okay, when I say hard processor system, every FPGA will have the same hard processor. It's not like that. For example, if you take Cyclone 5, we have a dual core ARM Cortex A9. Whereas when you go for Agilex or Stratix, we have a quad core application processor A53. Whereas in Agilex 5, we do have two different cores. One A55, then A77. Both are present. Along with that, you also have an FPGA. So you can imagine how big will be that. Is the point clear? So that means they are fine-tuned for a different application. That means the basic DSP blocks, the digital signal processing blocks, are replaced by tensor blocks. Then you can fine-tune that FPGA for an AI application. So that means we say that it is an Intel's, right? And the industry's first AI optimized FPGA. That means that particular FPGA can be used for only AI applications. That means there is a demand. That's the kind of applications we create. So that means that there are reference designs available, which you can definitely try and practice it. Okay, we don't have hardware, nothing to do, because the OpenVINO and the OneAPI platforms helps you to access these hardware in the dev cloud. So you can register in our dev cloud and you can get access free for 120 days with CPU, GPU and FPGA availability to test your algorithm. Right, you want more, then you can still extend. You need to provide some justification that why do you require and what kind of research you are doing it, they will still extend if required. So 6 months is a fair time where the students can complete the project also. Right, and then what is main when you say, I am going to explain you the last two bullets you can see. The Intel SoC FPGAs for AI and ML, and then I will also touch upon the SoC prototyping. What is the strategy Intel follows. Now, we know about Moore's law, I don't want to explain, but then I wanted to put that in a different perspective. You would have seen this. So, we say performance, power, area, and then cost. That's what we say. We call this as a PPAC. What is very important is, we want the performance should always be increased, and then you need to also ensure that there should be greater than 20% less energy switching. And then 30% less chip area footprint. That means you could see what is there with 28 nanometer Cyclone 5 and what is available with 14 nanometer Stratix or 10 nanometer Agilex. You can understand, okay, what is the dense present inside it. And the cost, okay, so that also is very important. For example, you have a low cost FPGA right now, and then you are trying some specific experiment and you say that, okay, I wanted to migrate to some other FPGA. Your next question would be, what is the cost of that? The point is, if we say that this is 10 times the cost of what you are using, you definitely don't want that product. Is the point clear? So the main question should be cost effective. That means everybody should try to experiment and try to use it. Okay, what is our roadmap? So this is our technology roadmap. The device which are available now, you can see that 10 nanometer superfin technology, Agilex, is available right now. Then you have products which are in pipeline with Intel 7 nanometer, 4 nanometer, 3 nanometer, and then we have products which are available in 2026-27 with 2 nanometer and 1.8 nanometer. We call that as an Angstrom era. So this is the technology roadmap, and now you can easily understand that, okay, the devices which we are going to get in 2024-25, how complex it will be, how dense it will be, and what kind of interfaces it can have, and how many number of processors will be there. You can just imagine. I have a question
regarding this Angstrom era. Below this 3 nanometers or around 20 Angstrom, what about the short channel effects?
Yeah, definitely there are so many number of short channel effects, but then still engineering has not come up with a solution. They have not identified and they have not given to the public like what is the effect. That's why it will definitely take 1 year time. For example, in 2024, we feel that the entire year would be, they will take time for research.
Because more and more the channels and almost source and drain will be about to overlap each other.
Correct, that's what.
So no switching.
Correct, right. So the challenges are always there. But then at the same time, they also have some other alternative arrangement to do that, and then they are also trying, Intel is also investing in R&D in multiple areas to see how that could be enhanced. And you know that the other foundry people will also would be trying a different set of logics like things, right? So you will get by 2024 August September time frame what Intel is exactly doing. You will be getting some exact details. But at this junction, only engineering team will know that what they are trying to do. Even the internal employee doesn't know what is happening exactly.
So this high K metal high K dielectric material we are talking the oxide layer or gate itself based?
No, it is at the outside layer.
Outside.
Right, so now let us get into the details. Okay, now why this particular slide, I'll just tell you. Earlier it was called as a system on a board. Now we are transferring that system on a board to system on a chip. That is an SoC. So to quickly get that perspective, okay, I'll just show you one more important scenario, because that will give you a picture what it was earlier and how do we try to. I'll just start from this place, then we'll go to the same slide again. So earlier what was the situation is, we had a CPU as a separate chip, FPGA as a separate chip, and then DSP as a separate chip. You know that for performing any digital logic experiments you use FPGA, and then you do some ARM keyed experiments, we require a CPU. For performing some signal processing lab, we require a separate dedicated processor, right? Now DSP. Now what happened is, like, we don't want all the three, right, separately. So what happened is, they tried to bring everything inside. So now the CPU goes inside the FPGA, and then you can also see that the DSP goes inside. Now when you see that the DSP also goes inside, now we have replaced all the external devices with the programmable logic. That's the logic. So what do you want to do? You need to reduce the cost, but then there are so many things included in the same complexity is there, but then yeah, challenge is definitely there, because it was the earlier 28 nanometer, then 20 nanometer mid-range device, then 14 nanometer, then 10 nanometer device. So it definitely shows you a clear picture that there are challenges, and that comes with the SoC now. So earlier what was the problem when you say, we have everything separate. Now we are integrating that into the same chip. That's the software. So now what is the advantage? Increase the system performance, reduce the power consumption, reduce the power size, and reduce the system cost. So that's the base thought process. So we don't require a separate chip for a specific one. So why can't you bring everything together in one chip? So that means you can think of an embedded application where you require hardware as well as software. I'll show in the afternoon. We can do a lab and see what we do in the hardware design and what we do in the software. So we need to do both. That means you need to perform a hardware software co-design, hardware software co-verification, and hardware software co-simulation. We need to perform both. No, I want to do only FPGA, you can still do that. I want to do only software, we can still do that. But we can also make communication between the FPGA and hardware. Now you need to create an embedded system. Earlier what was the situation? What is available on the FPGA side? You have one UART, only that you need to depend. You will be having some other peripherals in the processing system, in the hard processor system also. So you can use that particular components also to create an embedded system. So you can create a custom embedded system, right? And based on whatever resources that are available, you can pick and choose, and then you can develop an embedded system. Similarly, for high-speed signal processing, right, applications where you require a vast set of multiplications, we can think what goes into the hardware and what goes into the software. So you can do a system-level integration and see that, okay, it takes a lot of time. So high computation things, push that to hardware, so that the FPGA can do that because it has more number of DSP blocks. Right, so those kind of options can also be possible. Right, so that's the background. With that, I'll go back to the previous slide again. So what happens now? How do we call them when you say an SoC FPGA is nothing but ARM plus FPGA? So you have a dual core ARM Cortex A9 or you have a quad core application processor A53, whatever it may be, plus an FPGA if you have. That's what we call that as a system on a chip. So that's our objective right now. So how that system on a chip will help us? That's our basic thought process. Earlier, everything was separate, they were present in a separate chip, but all are integrated right now to get that specific value.